Hello, Mr. Tony. How are you? I hope you are fine. Concerning this course contains several lessons. The first four lessons tell you how to install and apply the toolbox. These four lessons. So the lesson one is about an introduction. Lesson two is presents the how the configuration of the platform can be done, and the third lesson how we use this platform. Finally, the fourth lesson presents the process of the experiments, the following experiments, which are stated here for the following lessons, lesson 5 till lesson 12. Yes. So let's start. Okay. The purpose from these lessons are to present the theoretical side of the following experiments. So the implementation will be performed using TeamViewer. However, the theoretical side or the process how the flow will go, this thing will be presented using these videos. Okay. Let's start with lesson 1, which is an overview, an introduction of the whole course. Traditionally, when you want to do an industrial task, you need several engineers and financial support with experience and resources with the following organization. Okay, but in the future, you need several drones or multicopters with a limited number of engineers which are called full stack engineers. These engineers, full stack multicopter engineers. These engineers, however, they are different than these because they are more experienced in the with respect to multicopters skills. So you need fewer engineers and less experience, which are doesn't need to be have a vast experience in different field, because they should be just focused on their role in the work. And you need also fewer resources because the number here is quite limited. Okay, however, these engineers should be full stack engineers. Full stack meaning they have the technologies and the skills. Which are these skills? What are these skills? So these skills have a theoretical side, which are should know. These engineers should know the airframe configuration, the propulsion system, the modeling, and etc. Concerning the practical side, they should know how to use the development tools, the operating systems, should know how to code, should know how to do software testing and flight testing, etc. So here there is a transition between the past and the future. These engineers previously people with background of electronics engineers, however, with the education in the future, the chief engineers are different, so they should know the previously stated theoretical and practical skills. So the word is changing. Now, concerning the plot, the tool, the rfly tool, which is the tool which is this course is about. The rfly tool, rflysim, is launched by the Reliable Flights Control Group. What is it? It is a tool chain, so it contains several tools. Each tool has its specific operation. Okay. The overall objective of the rflysim is to do reliable flight control. or to do the monitoring, controlling, and monitoring, controlling of drone system or the multi-copter system. This tool chain, what are the tools that are inside? There is MATLAB Simulink, which is supporting the full design phase, which is model-based design. Model-based design meaning that each subsystem is modeled, has a model inside the MATLAB or the Simulink. Simulink is a tool inside MATLAB. Simulink is a tool inside MATLAB. So here, where they use in this platform, they use Simulink. Simulink, which is a tool of MATLAB, Simulink is also used inside the rflysim tool platform. So it is a model-based design. It uses also Python, which is supported by rflysim platform for top-level vision and SWAP. Okay. rflysim ecosystem has many open source softwares and some tools which are developed by them. The core values of rflysim, what it can be done using this rflysim platform. We can do hardware in the loop simulation, meaning we can do the simulation inside the computer, or with using also a hardware which is connected to the computer. We will see this later, including Copter Sim we design and a real plugin model. This is just an example which will be seen next, which we will see next. Also, there is a hardware in the loop. Okay, this is what I was talking about, hardware in the loop architecture design. The education level of rflysim. This rflysim has an educational level version and a commercial level. Okay, the educational level focuses on the ease to access. So you can use this rflysim in your personal computers to run the model and serial ports for communication with the control board. In this course, of course, the educational level is enough. Okay. For the commercial level, it focuses on a reliable performance. It presents real-time simulator you use with the FPGA to run the models and sensor chip. So it is a more reliable performance with high accuracy. In this course, they said they just uses we can use only the educational level, so not to worry about the commercial level. Okay, the educational level rflysim it includes Copter Sim. It is a software which will be presented in the next lesson. And a real plugin. So what are the features of this version or this educational level rflysim? It is easier to use, distributed structures. So this to simulate a system, there are structures inside. Each structure presents its perform alone. We can do UAV swarm simulation, multiple vehicle types, high fidelity 3D environment, and vision-based control. Okay, these pictures present how the rflysim can be used. Mainly, they will be seen. We will see them next lesson. But as you can see, this is a multicopter, the controller. This is a platform, the interface, user interface, simulation. This is Simulink. Also, this is a Simulink in Simulink, and this one, it is a software in the loop simulation. Here, software in the loop simulation meaning we need only software to simulate the system. Here, for example, there is MATLAB Simulink in the PC, and there is Flight Gear 3D. It is also a software in the PC. So in this way, we can simulate the objective of a certain experiment. Also, there is a hardware in the loop simulation where they use both software with a real hardware, connected hardware, of course. And there is also flight tests, which are completely hardware tests. However, we will see that hardware tests are not somehow they are ignored because in the lecture because of their of okay, we will see this later. rflysim. For rflysim here, these pictures present some samples of the following experiments. So we can use swarm hardware in the loop simulation framework, where each computer is connected to several multicopters are connected to a computer, and these computers are connected with a network. This network uses a protocol called UDP. These things will be we will see them in the future. Okay, also these just are some pictures from different tools that I have already said about it. I said in rflysim. So this is MATLAB, and this one this is hardware, and this one uh, is a software that presents to you what when you control the multicopter, what you will see in the computer or in the simulation. Okay, the commercial level rflysim, it includes model and hardware in the loop architecture design. So we need to use model in the computer. The computer is connected to hardware devices, and the simulation is carried on inside the computer using the model. However, for the part where for the parts or for the object where there is no model, the computer will use the real hardware to get to process in the flow of the simulation. What this commercial level present or propose or offer, the commercial level rflysim offer more extensibility, practicability, and standardization with automation. So using this level or this version, you can extend the presented simulations in this course, but it is not necessary to use it to do the task in this course. However, if you want to extend your what you want to do, you will need it, but it's not part of the 12 experiments. These pictures present also just a screenshot from the presented tools, or the tools will be presented in the next lessons. So as you can see here, the Flight Gear 3D visualization program, here the fault injection automatic safety testing program, and this is a lab view model state display program, and this is a hardware connected to a computer. Camera view for autopilot system. Yes, this is the autopilot. Okay. Now we move to the course design. But the course is designed with a practical side. The practical side contains experiments. The experiment content and framework design are as follows. So there is a proportion system design, there is a dynamic modeling, and there is a dynamic modeling and sensor calibration. Then we have state estimation and filters. So as you can see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, state estimation and filter design, attitude and counter design, etc. You can see in this figure we have sorry. Okay, you can see in this figure there is a design. There is 8 experiments. Okay, each couple can be categorized for a certain objective. The first couple, the first and the second experiment are for the design and modeling experiments. This is the objective of from these 2 experiments is to model the proportion system design and the dynamic side of the system. So it is when we start from the hardware and we go to modeling. So it's a modeling part. Yes, it is called modeling experiments, design and modeling. Then we go when we have a hardware, we have then we model it in the software. After modeling the hardware, we need to take the data. So we need to do estimation of the for example the wind, etc. The speed of the proportion system, etc. So this data can be taken or they can be captured using sensors. However, these sensors need to be used after a calibration. So we need multi-copter sensor calibration, then multi-copter state estimation and filter design. So this one is to model the hardware. After modeling the hardware, how we can estimate and and filter the design or the data captured from this model. And after that, we get to the control experiment. Here, the control experiment, meaning these 2 experiments, 5 and 6, multi-copter attitude controller design, how we can control the attitude, and then multi-copter fixed position control. So how we can control the multi-copter to be in a fixed position in the space. So these 2 experiments are for the controlling experiments, controlling objective, for the control object as an objective. Yes. And finally, we get to the fourth section, or if it is alright to say that, the fourth part, which is a design making experiment. Yes. So this, after getting or designing how the control process in the third section, we go to the design making experiment. So here, how the multi-copter, you how we can make decision for the multi-copter, decision making controller design for semi-autonomous multi-copter. Multi-copter fails safe logic design. If it is failed, how what are plan B, plan C, etc. I hope figure or this image presents an overview what are the eight experiments are about. Yes, so let's move. Yes, this next they will present how we can use the course design. The course design, yes. So we can the author of this PDF say that we can use start by design mode and modeling experiment. Then we go to control experiment. Then we go to decision. So this is the model. Estimation of the data, the real data, estimation of real data. Yes, so it is really theoretical. So we get an estimation. Yes, so it is a model, estimation, control, and decision making. So we can just do the modeling, then we go to experiment or the control, then we go to the decision making. Or another flow, we can go, as I said previously, we can go modeling, then we go to estimation, then we go to control, then we do decision making. So these are just how if we can ignore this part or not. However, I will present it. So we will follow this one to cover all the experiments. This one. Okay. Now, for example, inside when we go from multi-copter proportion system design, then we go to experiment 2, which is about multi-copter modeling. Here we need to do different design schemes used for the modeling. We need to know this. So there are different type of multicopters. So these different type of multicopters have their own properties, such as the mass, etc., gravity, acceleration, gravity, etc. These parameters are needed to be used inside the software, or inside the software which will be presented next. Okay. Now for the experiment step design, which is this one, for example, here. Yes, for the experiment step design, when we do an experiment, generally each experiment has a basic experiment for each course, for each experiment here, for this one or this one or this one. Okay, it has 3 levels. It has basic experiment, analysis experiment, and design experiment. For example, if I open the file for another for experiment, let's say 7. Okay, I give here what we will see: basic experiment, analysis experiment, and design experiments. Okay, so each experiment has 3 parts: basic experiment, analysis experiment, and design experiment. The basic experiment contains software in the loop simulation, which is completely in the your computer. Then we do a hardware in the loop simulation. Hardware in the loop simulation, meaning the autopilot. We will use the autopilot hardware that you have, which is connected to your PC. So the object, the modeled objects in the software in the loop simulation, some of them will be removed, and instead of the removed object, the computer will use the autopilot, for example, which is connected to your PC. Okay, so this one is more realistic than this one, but this one is just in the computer, as I already explained this previously, and we will see that in next lessons. So there is always software in the loop simulations, hardware in the loop simulations for each part. What is the difference from these 3 experiments? We will see this later in the future. Yes, that's it. Experiment step design. Basic experiment. It is open. You need here just to open the given code example and run it just like that. And run it when you see how it is run or it is perform, you get a first idea how the work is done. So it is just simple. Open and run. Because the source code is directly given, and record the results to verify that you are running the experiment correctly. Then the second part for each experiment is the analysis experiment. Here we need to modify the given code example. Here the given code example from here is given. We need to modify it in order to do a job, a certain job. Then we get to the design experiment. Here the design experiment, we need to do the design. The design meaning the author of this PDF will give us a task, and we will do the design independently. The course design, all codes are implemented in a real flight test. Yes, because all the codes are already tested. Yes, here the development platform, all the experiment uses the platform. The analysis process, it is needed for the analysis experiment and the design experiment. These three experiments are basic, analysis, and design, which I was talking about here. Yes. So the analysis process should be done in the analysis experiment and the design experiment. Mainly because the design experiment is the we will use all the parts. Yes. And then we have the design method where the design experiment is checked. Concerning software in the loop simulation, this software in the loop simulation will be used in all the experiments: basic, analysis and design, hardware in the loop simulation also, and flight test also. Teaching design, modifying the goals in the propulsion system design and modeling experiments. The different progressive studying routes and opening new experiments. So here in the course, we can in the future, you can in the course you can modify the course in the propulsion system. Here, for example, these different propulsion systems, different multicopters. So you can modify the propulsion system that suits you. Yeah. We can also use a different progressive routes, which I already presented before. As a conclusion, from this course, you will answer, or we will answer these questions. Given a payload and flight endurance requirements, how design a multicopter propulsion system? This is mainly from experiment 1. Given a Pixhawk autopilot, how calibrates its accelerometer and magnetometer, and how design the filter to estimate the state? This is the calibration, experiment. So these questions will be answered with the flow during the flow of the future experiments, the future lessons. Question 8. Given a new algorithm, how to realize it by the model-based design? Okay, so this is important. You can have your algorithm, developed algorithm, but first you need to check it in the model-based design, then the hardware-based design, then finally you go to the practical tests or flight tests, real flight tests. Then question 9, how new functions are developed based on the platform, such as health evaluation or vision-based autonomous flight. This is different applications where you need just to flow the functions or the objective from using these multicopters. Given a group of engineers, how to organize them effectively. This is an extended work from this course, which can be done based on the objective from developing these multicopters. I hope this part, as it is an introduction, it doesn't contain any coding, or so we don't need the team viewer. So I hope it is clear. If you have any question, just state the timing, and I will explain more. I hope the recording was good, so thank you. Hello. Okay, let's start with the second lesson, lesson 2, which is about experimental platform configuration. It is about the configuration part of the platform. The configuration meaning it will contain several configurations which will be done in TeamViewer. Okay, let's start. The outline, we start by an overall introduction, followed by the software package installation and hardware platform configuration, and finally the summary. Generally, the software installation will be done in TeamViewer. The hardware configuration, I will instruct you based on this PDF or this PowerPoint, okay, during TeamViewer. So it is we will do the overall introduction, which will present all the needed tools from rflysim platform. This platform, yeah. Okay, as an overall introduction, the experimental platform can be divided into two parts. There is a hardware platform and a software platform. This lesson should introduce the basic component of each platform. So the hardware, which is a software, which is the hardware that you have, for example, the autopilot, etc., and software platforms such as MATLAB, Simulink, and other softwares. Noteworthy, this lesson is mainly for independent readers. So this lesson it is used to present or to introduce or to prepare the platform, so it is for independent reader or experimental course teachers. The platform should be prepared in order to be used in the next lessons, of course. Hardware platform. Okay, the hardware platform and the software platform are presented on the right. As you can see, the hardware system contains the autopilot, the radio controller, transmitter and receiver, also with a PC with the controller. The controller, the radio controller, the transmitter and receiver with the PC and the controller, okay, with the autopilot, yes. So, okay, the basic configuration requirements for your PC, your personal computer. It is Windows 7 or newer, 64 kernel system. The processor Intel i5 or above, memory 8 giga or above. Graphics are here, 2 giga or more. Storage 30 giga. And interface at least one USB because we will use the hardware. And monitor, of course, the screen monitor, yeah. And also we need also the rflysim platform, which I suppose you have already downloaded the platform. We will see this next. The hardware platform, okay, because all control algorithms are eventually deployed in a real aerial vehicle to perform flight tests. A hardware platform must be prepared for the basic flight test requirements. As shown in the right picture, the experimental hardware platform recommended in this book is composed of 5 main parts. Okay, so as the hardware platform, the hardware side contains, as I said, airframe system, which uses the arm, the fuselage, and the landing gear. For the propulsion system, which contains the motor, the battery, the propeller, and the ESC, which is the controller of the motor. Yeah. The radio, also the radio control system, which is just the radio control transmitter, radio control receiver, and the charger. The autopilot hardware system, the autopilot with the USB to be connected with the PC, and the GPS receiver. So this is the 5 hardware, the main parts of the hardware platform that you should have in order to do all the experiments. The hardware now each part will be explained individually. Ground computer, this one. It is a high-performance personal computer with an operating system that performs 2 main tasks: providing the software operating environment for the simulation software tools to perform functions such as control algorithm development, system in the loop simulation, automatic code generation, and hardware in the loop simulation. So this is a really the work will be done in. Because MATLAB, Simulink, several tools are installed there, are configured here. We will see this in TeamViewer. Also working as a ground control station in outdoor flight tests to achieve functions such as sensor calibration, etc. So besides, it is used to install the different tools such as to do the system, the software in the loop simulation and using Simulink, etc. We will use the PC to do the to do the sensor calibration, etc. These functions. So it is really focused or centralized using the system is centralized based on the operating of your PC. It is as for example as the brain, yeah, of a human. Okay, for a hardware platform. Okay, hardware platform, autopilot system, also called flight control system. Here, other unit as you the second part, which is autopilot, GPS receiver, and USB cable, as the operating platform to connect it to the PC. As the operating platform of control algorithms, it has many sensors and powerful computing capability. This is the most very important powerful computing capability to estimate flight state and calculate the control signals for the propulsion system to realize the flight control of multicopter. So this lesson selects a widely used open source autopilot. It is PixHaw as the development and the experimental autopilot system. However, there are different types. They are presented, and you need to know what you have in order to be used in the configuration. Yeah, we will see this later. PixHaw is an independent open hardware. This one is an independent open hardware project that aims to provide standard, readily available, high quality, and low cost autopilot hardware for education, amateur, and developers. For different flight missions, performance and cost requirements, the PixHaw provides a series of autopilot hardware products that highly promote the development of multicopters. Now we move to the third part, which is a radio control system. It is simple, just a controller. We need where you do the controlling side as a human. Okay, so you need a transmitter, also a receiver with a charger. Yeah, the radio control system. It is a radio control transmitter, receiver, and a battery charger. It is used to send a control command from the pilot on the ground to the autopilot system to realize remote flight control. Yeah. The propulsion system, it includes this one, the propulsion system. It includes a battery, motor, and the controller of the motor with the propeller. Okay, electronic speed controller of the motor. Yeah. And motors. Okay, the propulsion system is used to receive the pulse width modulation. So this system will receive a pulse width modulation. You know it. It's function like this. Okay, we will see it later. This signal is used to control the speed of the motor. Okay, from the autopilot system and control the movement of a multicopter with the thrust and torque generated by the rotation of the propellers and motors. Okay, now it remains the last part, which is the airframe system. Oh, sorry, the airframe system. It includes a fuselage and landing gear and several arms. As you know, I suppose you have it. Yeah, you told me that you have it. The airframe is used to support the propulsion system, so the propulsion system will be installed here, and using the autopilot will be connected will be connected with the radio controller. The radio controller, using the radio controller with the autopilot, we will control the speed of the motor. The motor which is installed in the airframe system. So the controlling of this airframe system is performed by this way. Okay, the airframe is used to support the propulsion system and the autopilot system and carry a payload. Okay, thus it is required to have an excellent aerodynamic performance and a structural strength to ensure that flight missions are successfully and reliably accomplished. This is I was talking about is the hardware part. Now we move to the software part. This platform supports all versions of MATLAB, but MATLAB above 2017B. You told me you have 2021, so it is or 20. Okay, there's no problem as stated here. The recommended installation is 2017B because they have tested using this version. This lesson do not provide the MATLAB installation package or the instructions how to use it. Okay, when you install MATLAB in your PC, majority of people install all the toolbox, but if you selected the custom installation, you need to install this list of toolbox. These toolbox are toolbox of MATLAB. Yeah, Simulink is here as you can see. Simulink code. Yes, Simulink. This one. Simulink. Yes. Okay. This experiment platform relies on software tools to realize controller design, code generation, autopilot code compilation, hardware in the loop simulation, and other functions. The simulation software package to compilation along with this book has a one-click installation script, a one-click, which will be done in TeamViewer. Yeah. Readers can click the script to finish all the installation and configuration process of this required software environment. The MATLAB Simulink and the simulation software package comprise the software platform, which contains the following. As you can see here, the software platform contains MATLAB Simulink, the flight gear, which is we will see each part or each software alone next. Yeah, as you can see, this one is to do this. It is a simulation of the space where the drone or the multicopter will move. Okay, this is a Simulink PSP toolbox. It is a Pixhawk toolbox, which is created specifically for PSP. PSP it is the software part of the autopilot. Yeah, of this one. Like computer we have Windows software and a computer. This is the hardware. This is the hardware and in the software side we have PX4 firmware source code. This is this one. This software is the software part of this hardware of the autopilot hardware, and this toolbox is used to specifically for this one. Okay, this toolbox is included in MATLAB. We will install it in MATLAB. Yeah, I don't need TPS. No, it's not here, so it will be installed. Yeah. Okay. Then Eclipse, we will see each software alone. Eclipse is a C++ editor where you can read what you have written, your code, your injected code in this system, this software using this Eclipse. And these tools are compiling tools. For example, when you install Windows in your PC, you have used the other third party or other software to install the window, to install Windows in your flash disk or USB drive. Then you use the USB drive to install it in your computer. The same idea here. This tool will be used to install the firmware in the hardware. Yeah, similar. Okay, this is a 3D display, and this is a controller for the sensors, QGC, which will be seen later. This copter sim, which is a simulator for the copter, the quality in the perspective of hardware properties, such as the mass, etc. Yeah, they will be presented each one by one. Yeah, this is the hardware, as you can see. This one is repeated. Is repeated. Okay, this the hardware I already talked about. Okay, let's start the PixHawk support package PSP toolbox. This one, it is as I said. Mainly, I think I said everything. Let's just check. It is a Simulink toolbox officially released by MathWorks for controller design, code generation, and firmware upload of the PixHawk autopilot. We have made some updates and optimizations based on the official PSP. This is important. So they have changed they did updates on the PSP toolbox, which is provided by MATLAB. So you need to install it using from them, not from MATLAB company, to ensure compatibility with the latest PixHawk and MATLAB versions. Yes, I said this. Okay, flight gear. This one, sorry, flight gear. Flight gear, which is just a flight simulator. It is a popular open source flight simulator that can be used to easily observe the flight states of a simulated aerial vehicle in Simulink by receiving flight data from Simulink via a UDP, user datagram protocol, which is in communication field, a network. In network, this protocol, which is used in the interfacing between two softwares, yeah, or two hardware, yeah, it is. Okay. So there's also PX4 software, which is the soft part of the hardware of the PixHawk autopilot. This one, as I said before, it is the source code. Is an open source flight control software system. What does it do? It runs on the PixHawk hardware platform. The PixHawk hardware plus PX4 software constitutes an integrated autopilot system. So these two work together, which is one of the most widely used autopilot systems for aerial vehicles. Now we move to these two. Okay, PX4 toolchain, this one. Compiling environment. It is used to compile the PX4 source code, this one, along with the controller algorithms generated by PSP toolbox. So the algorithms will be generated using this toolbox, as we will work using Simulink. Our work will be done using Simulink. The algorithm will be generated using this toolbox in MATLAB. Then this software, the compiling environment, this one, will generate the PSP toolbox into a .px4 format. So this software will generate the source code of this hardware with the algorithms that we have already designed. Both of them will be injected or installed or configured inside the hardware in this form. .px4 format firmware file. Then the firmware file is uploaded and burnt into the PixHub autopilot hardware. Exactly, yes, it is similar to PC. To control the control algorithm generated by the PSP toolbox, this one PSP toolbox, will automatically run after PixHub, just a restart of the hardware. Eclipse C++. It is an integrated development environment. It is just used to read and modify the PX4 source code. Eclipse C++ is a compact C++ IDE with functions similar to those of Microsoft Visual Studio. I think, as you know, as you told me, you know the C++. I think so. You know what is Microsoft Visual Studio. It is a compiler, yeah. Okay. Now we move to the tool, sixth tool, which is a ground control station. This one, QGC, ground control station. Q ground control. It is used to perform the pre-flight tasks. So before the flight starts, we need the sensor calibration, parameter tuning. This will be done using this software. For the PixHub autopilot before the multicopter takes off. Okay, the QGC is also used to receive the flight states during its operation and send the control commands of the multicopter through wireless radio telemetry during flight tests. And we have also finally CopterSim. CopterSim is a real-time motion simulation software. It is a real-time motion simulation software developed for the PX4 autopilot system. Readers can configure multi-copter models in the CopterSim, so the modeling in the following experiment. The modeling will be done using this software, the CopterSim, and connected to the PixHub autopilot via the USB serial port to achieve indoor hardware-in-the-loop simulation. Yes, 3D, 3D display. 3D display is just a visual display software. It is a real-time 3D visual display software. It receives the flight data and of CopterSim. So the flight data are followed from CopterSim to 3D display. This is just for display, yeah. Through the UDP protocol. This is a protocol in communication and networking field to display the attitude and the position of the multicopter in real time. CopterSim and 3D display together constitute the integrated hardware-in-the-loop simulation platform. The distributed independent operation mechanism of CopterSim and 3D display provide future compatibility for swarm simulation. Okay, now we have arrived to the installation steps. This part will be done in TeamViewer. So I suppose, I don't know if you have already installed this package. Yes, if not, you are supposed to install it, to download it from this link. Okay. Are supposed to download it. After downloading this one, then we will follow from MATLAB, and you already, as you told me, you already installed MATLAB 2020 or 2021. Yes, from MATLAB we will install the whole package or the whole platform in one click, as they said. The steps are stated here or are presented here: 1, 2, 3, 4, etc. We will follow them one by one. Yeah. Here, next, okay. How to download what I was talking about it here. This one. I follow the link now. You need to fill this information in the site websites and get download link. Then the link will be will be sent to you based on the stated email here. Sorry. Okay. Then you can download the link. You can download the file. Yes. So yes, this one point. Another point, which is here. Yes, I already said it here. You need to identify which picks the autocontroller, the autopilot that you have, because there are several types, as you can see from this list. I don't know what you have. So, okay, in TViewer we will start from here, from slide 17, from here, and we will follow it. As you can see, it is just a step, one by one, one by one, one by one. All the work is done step by step from based on this one. Till the end, yeah, till the end, as you can see. I hope this lesson is clear, but what is remaining is the TeamViewer part. It is the implementation parts. Okay, thank you.